all right? So we're going to go through all these different relationships so that we have a good understanding of the way gases behave, which means we're going to have to take some data and we're going to have to graph that data in order to figure out their mathematical relationships. Now, this is more like physics than it is chemistry. Really, it is. We're not talking about chemical reactions. We're not talking about mole ratios or balanced chemical equations. We're talking about the physical relationship between two variables, pressure and volume of a gas. And that's what physicists do. They do experiments, they get numbers, they make a graph, and they see if they can come up with a conclusion about the way that behaves. So before we can get some pressure and volume data, which we will get at the end of the class, I want to talk a little bit about some relationships that we are going to encounter in this class. Now, the first possible relationship that we're going to deal with is a direct relationship. For all direct relationships, as one variable increases, the other variable increases. So we're going to get some data, and we're going to plot it, x versus y. We're going to make a graph, and if we've got a nice straight line, we can then say that y is directly proportional to x. That's the statement we make. When we have a nice straight line, we can say that y is directly proportional to x, and we represent it with this little symbol right here that might look like an A, but it's actually a Greek letter. It's an alpha, and if you draw it, maybe elongated, it looks a little bit like a fish. And that's the symbol that we use that essentially says is directly proportional to. So if we get a straight line, we can make the statement, y is directly proportional to x. This is really basic linear mathematical analysis. Now, we know that the equation for a line, well, again, good old math, they know how to indoctrinate, I tell you, but I'm getting there with my molar math, but I'm not there yet. Equation of a line. Oh, that's fabulous. You guys are great math zombies. Y equals mx plus b. In our graphs that we're going to encounter, they will always run through 0, and therefore, what can I say about this equation? If they all run through 0, yeah, I can get rid of the b, and I can just say y equals mx, all right? Math likes to use m that represents, what does the m represent? The slope. Science, for some reason, we like to use k as a constant. It's just something that in many scientific things that you have k as the constant. So I'm going to write the equation as y is equal to some constant k times x, where I've simply switched m for k. So if we have a straight line, we can make the statement y is directly proportional to x. We can shorten that up with this nice little symbol, y is directly proportional to x. And we can make an equation, y is then equal to some constant times x, all right? And that constant there is still indeed the slope, all right? And if we wanted to do some deeper analysis, we could use that, but we're not going to get into that. Grade 12 university physics, you'll do all kinds of neat stuff. That says slope, and I wanted it to point at that k. There it is. That's better, okay? Now I want to talk to you about something that in science we call the relation equation. I don't know what you call it in math, but in science I call it the relation equation. We can relate 2 points on the line, all right? And we can generate a useful equation from that. We can call the first point, good old math, x1 comma y1. And we can call that second point, good old x2 comma. Each of these points exists on the line, and therefore I can put them into my equation. Y1 is equal to k times x1. And because it's on the same line, I can say that y2 is equal to k times x2. Right? Those are just 2 points that are true for that line. Because they're on the same line, k is the same for both of them. So I could actually put those two equations together through the k. I'm going to divide off the x, and bring it down here. So I'm going to have y1 over x1 equals k. I can bring this x down here as well, and I can get y2 is over x2 is also equal to k. All right? And because we're on the same line, the k's are the same, so I can make the statement y1 over x1 equals y2 over x2. All right? And that right there is what we would call the relation equation. Relation equation. Why? Because it relates 2 points on the same line. It means that if I have two variables, at one point I know the information, and I know where I want to go for one of the other variables, I can always solve for that fourth unknown guy. All right, I can always solve for that. I'm going to rearrange this relation equation just to show you one other interesting thing. I want to bring the y's to the same side and the x's to the same side. So I want all y's on one side and all x's on the other side. I'm going to bring this y2 over to the left, and that means it's got to go on the bottom because I've got to divide it off. And I want to bring this x that's on the bottom over to the other side, and that's going to bring it to the top because I've got to multiply it when I bring it to the other side. So that means I'm going to have y1 over y2 is equal to x1 over x2. Now that's also another version of the relation equation. There's nothing wrong with it. I like the way this one is because it keeps all the ones and twos together. But you can see that it's linear and direct as opposed to inverse, because my next equation is going to have an inverse relationship. But you can see that it's a direct relationship because I've got the ones on the top and both of the twos are on the bottom. The next relationship that we possibly can run into is indirect. And again, there are many indirect relationships, but the specific one we're going to look at is inverse. For all indirect relationships, as one variable increases, the other one decreases. It's indirect. It does the opposite. When you graph an inverse relationship, you get a curve that looks like this. Because as as x gets big, y gets small. And if x is small, y is big. The opposite, the inverse. If you see a curve like this in your data, I want you to say to yourselves, oh, if I get a curve like that, I know that y is inversely proportional to x. And I can say that y is directly proportional to the inverse of x. So it's related to the inverse of x. I can go from this proportional statement to an equation, just like I did on the last slide. I can say that y is equal to some constant divided by x. So I just put a constant in, just like I did before, but now x is on the bottom. Again, I can deal with 2 points, x1, y1, x2, y2. And I can do the same with the equation for this one. Before I put them in, I'm going to move the x. If I have an inverse or indirect relationship, then in this case I'm going to have y times x equals k, because I brought the y up to the x to the other side. Now I can say y1 times x1 equals k, and I can say y2 times x2 is also equal to the same k. Because they're on the same curve, the k is the same, and therefore we can say that y1 times x1 equals y2 times x2. And that is the relation equation for an inverse relationship. Relation equation for inverse. I just want to rearrange this inverse one around just so that we can compare it to the last one. I want all the y's on one side and all the x's on the other side. So I'm going to bring this y2 down to the bottom. y1 over y2 equals, because I brought the y2 down here. And I'm going to bring this x1 down over here. That means I've got x2 over x1. And when you put it in this form, you can see that it has to be inverse because I've got 1 on top of the one side and 2 on the other side. In other words, it's like something's been flipped. It's inverse. Okay?